we've all heard of the Fibonacci numbers before, and the main object in this video is to derive a closed formula for the nth Fibonacci number. And what I mean by that is we're going to derive a formula in which if you plug in, say, n equals to 1,000, this formula directly gives you the 1,000th Fibonacci number. And the cool thing is, you don't have to figure out what the previous terms are. Alright, so let's get started. First of all, recall what is the recursive definition of the Fibonacci numbers, i.e. what is the usual definition of the Fibonacci numbers. It's this. And second of all, we need to know what a difference equation is. The difference equation is this, and we're going to use the vector matrix form today. It's the current vector is equal to a matrix times the previous vector. And what we're going to do is we're going to convert this thing into a matrix vector difference equation. And using that, we have to use the diagonalization of A, in which the prerequisite is probably you need to know about eigenvectors and eigenvalues. And we're going to derive the closed formula. So there's a lot of intermediate steps, but don't worry, I'll guide you through this. So how do we construct this beautiful interconnection between these two numbers? What we're going to do first is we're going to construct a system of equations. Alright, so let's first copy the recursive definition of the Fibonacci numbers. And let's define u of k to be f of k plus 1 and f of k. That's pretty trivial. We didn't do anything weird over here. We're just defining a vector. So let's write this over here. So f of k plus 1 is equal to itself. What we've derived over here is a matrix vector multiplication. That's where the matrix originally came from, right? So we can directly write this as f of k plus 2, f of k plus 1 is equal to 1, 1, 1, 0. That's our Fibonacci matrix. Let's call it A, because A is our usual variable for the matrix, times f of k plus 1 and f of k. Okay, that's cool. And notice that this is simply u of k plus 1, and this is simply u of k, right? These are what we defined to be u of k. So, now, see that we directly derived a difference equation from our Fibonacci definition. But you might be wondering, what's so good about this difference equation? Why am I talking about difference equations right now? So let's see what properties the difference equation exhibits. Alright, so let's first consider u of 1. What does this equation tell us for u of 1? Well, u of 1 is equal to a times u naught. Alright, what about u of 2? U of 2 is a times u of 1. But look, u of 1 is simply a times u naught. So we have a times a u naught. And this is a squared u naught. Okay, now what about u of 3? U of 3 is equal to a times u2. But u2 is a squared u naught. So we can directly substitute this in. A squared u naught. And this is equal to a cubed u naught. And so we can directly derive a formula. U of k is equal to a to the k u naught. Right? U of 2 is equal to the second power of a, and u of 3 corresponds to the third power of a, and so u of k corresponds to the kth power of a. Fantastic. But now, there's still a problem, right? The thing is, we don't have a nice formula for a of k, and so what we're going to do in this step is to diagonalize a, assuming that a is diagonalizable. Okay, how do we diagonalize this? Well, we simply want a is equal to the eigenvector matrix S times the eigenvalue matrix lambda and S inverse. And this is essentially equivalent to stating that a to the kth power is equal to S lambda to the kth S inverse. Let's see, lambda to the kth is a nice formula, right? because lambda to the k is simply all of the entries on the diagonal to the kth power. That's it. And so what we're going to do is we're going to diagonalize our Fibonacci matrix A. So let me just write what we're going to do. We're going to diagonalize A. To do this, we must find the eigenvalues and the eigenvectors. So first of all, let's compute what its eigenvalue are based on the traditional method. So we have to calculate what the determinant of A minus lambda I is equal to 0. So that's the usual way of computing it. Okay, so I'm not going to get into the details over here, but this directly yields us lambda squared minus lambda minus 1 equals to 0, equivalent to stating that lambda squared is equal to lambda plus 1. The greater solution to this quadratic is the golden ratio. And let's solve this. Solving this quadratic using the quadratic formula, or completing the square, gives us lambda, our eigenvalue, is equal to 1 plus or minus the square root of 5 all over 2. And let's just write this as lambda 1 is equal to 1 plus the square root of 5 over 2. Notice that this is equal to 5, but we're not going to write this right now because we kind of need its numerical value. And lambda 2 is equal to 1 minus the square root of 5 over 2. Fantastic. So that's basically it. We have calculated the eigenvalues, and we can put them in an eigenvalue matrix. Lambda is equal to 1 plus the square root of 5 over 2, and 1 minus the square root of 5 over 2. And lambda to the power of k is 1 plus the square root of 5 all over 2 to the kth power, and the same thing over here. Now we need to calculate what the eigenvectors are. And how do we do that? Well, it's simply acknowledging what A minus lambda I is. A minus lambda I is equal to 1 minus lambda, 1, 1, and minus lambda. And we're trying to find what the null space of this is. We're trying to solve this equation. Okay, so let's notice that we can write x as x1, x2 as its components, that's equal to the 0 vector. And this is simply equal to x1 times the first column of our matrix plus x2 times the second column of our matrix. Okay, and notice why I'm not using the values over here. It's because the values are quite messy. They're quite hard to, manipulate around. So we're just going to use the general version of the eigenvalue. And actually that kind of works. So notice that if x1 is equal to lambda, so the eigenvalue itself, we have this. If we set x2 is equal to 1, we directly have the second column without any scalar multiple. And this directly yields us lambda minus lambda squared plus 1, and then lambda minus lambda. Well, this is equal to lambda squared minus lambda minus 1 all to the negative, and this is 0. And now you might wonder, what is this doing here? What is this? Well, this is simply what we got by setting the determinant of A minus lambda I equals to 0. And this is equal to 0, right? This expression is equal to 0. So we have minus 0, 0, which is the 0 vector. Fantastic. Now we have derived what the eigenvectors are, right? The eigenvector is when setting x1 equals to lambda and x2 equals to 1. So our eigenvector x is equal to lambda 1. And what does that mean? Well, that means that our x1, our first eigenvector, is equal to 1 plus the square root of 5 over 2, 1. And x2 is equal to 1 minus the square root of 5 over 2, 1. Fantastic. Now, let's put this in an eigenvector matrix. S is equal to 1 plus the square root of 5 over 2, 1, and 1 minus the square root of 5 over 2, 1. Nice. And now what do we have here? Well, we have S and we have lambda known. And so we have to calculate what S inverse is. Let's first notice what we have by directly substituting a to the k the power over here. Well, u of k is equal to a to the k u naught, which is equal to s lambda to the k s inverse u naught. And we can directly calculate this, right? Alright, fantastic. So we need to calculate what u naught times s inverse is. We already know u naught, right? U naught is equal to the first Fibonacci number and the 0th Fibonacci number. And that's 1, 0. Right? Looking over here, the 0th Fibonacci is 0 and the first Fibonacci is 1. So let's calculate S inverse. S inverse is equal to 1 over the determinant of S times its cofactor matrix transposed. You can use other methods to calculate what S inverse is, but I'm going to use the cofactor rule. Okay, over here we have, let's see, we have 1 over the determinant of S. And notice that this is simply lambda 1 and this is simply lambda 2. So, we can write this in simple terms as lambda 1 minus lambda 2. And what do we have here? Well, we have the cofactor matrix transpose. So what is the cofactor matrix? The cofactor matrix is simply all of the cofactors on its entries. So this is the cofactor 1, 1, cofactor 1, 2, the cofactor 2, 1, and cofactor 2, 2. So what's cofactor 1, 1? Cofactor 1, 1 is when this is removed and its rows and columns and we only have 1. And I'm assuming that you know what the cofactor is from linear algebra, so I'm just going to derive this. So we directly have minus 1 minus lambda 2 and lambda 1. That's our S inverse. And we need to transpose that. So our final equation for S inverse is 1 minus 1 minus lambda 2 lambda 1. Now, what is lambda 1 minus lambda 2? Well, lambda 1 minus lambda 2, the difference of the eigenvalues, is 1 plus the square root of 5 over 2 minus 1 minus the square root of 5 over 2. And what's that? That's 1/2 plus the square root of 5 over 2 minus 1/2 plus the square root of 5 over 2, which is these two cancels out, and we directly have the square root of 5 itself. Beautiful. And so we can write this as 1 over the square root of 5 times this matrix. Now we have derived what S inverse is. And so what we can do is we can substitute all these matrices inside and calculate what UK is. So UK is equal to S lambdas to the K, S inverse U naught. And what's S? S is this thing. So let's write this as lambda 1, 1, and lambda 2, 1. What's lambda to the K? Well, lambda to the K, let's see, is this. So we can directly give 1 plus square root of 5 over 2 to the K and 1 minus the square root of 5 over 2 to the Kth. I'm going to move this down because it's going to take a bit of space. And what's S inverse? Well, it's 1 over the square root of 5 from this thing, right? Our answer is this, times 1 minus 1 minus lambda 2, lambda 1, and u naught. U naught is 1, 0. Okay, so let's calculate this using our traditional matrix multiplication method. First of all, let's multiply these together, because matrix multiplication is associative. Alright, so let me just copy all of these over here. And then we have 1 over the square root of 5 times, let's see, we have 1 and we have minus 1. That's it. Okay, so let's multiply these two first matrices together. And this gives us, let's see, notice that lambda 1 is simply this thing inside the power. And this is a diagonal matrix, so I didn't write the zeros. We directly have 1 plus square root of 5 over 2 to the k plus 1. 1 minus the square root of 5 over 2 to the k plus 1. And this matrix is not large enough. 1 plus the square root of 5 over 2 to the k, and 1 minus the square root of 5 over 2 to the k, close brackets. And now we can take this constant multiple out front and this vector. Now what do we have? Well, we can directly multiply this matrix and this vector, giving us 1 over 5. What do we have here? Well, we have 1 plus the square root of 5 all over 2 to the k plus 1 minus 1 minus the square root of 5 over 2 to the k plus 1. And we have 1 plus the square root of 5 over 2 to the k minus 1 minus the square root of 5 over 2 to the k. Fantastic. And notice that this is equal to our u of k. And what's u of k? Well, we defined u of k to be f of k plus 1 and f of k. Now notice something. F of k, this one component, is equal to all these things. And so, we have reached our closed formula. What is f of k? Well, ignoring all of these top terms, we directly have f of k is equal to 1 over the square root of 5 times 1 plus the square root of 5 over 2 to the k minus 1 minus the square root of 5 over 2 to the k. Okay, now here's where things get really interesting. Notice that we can write this as 1 over the square root of 5 times phi to the k, where phi is the golden ratio, minus phi bar to the k, where phi bar is simply this other version of our quadratic solution. Beautiful. Now we have the formula for our Fibonacci number. And this is really interesting, because notice what this formula tells us. F of k is always a natural number. And this means that all these square roots and powers, they all combine to give one natural number. And this is really interesting, right? And it also gives the power of what the golden ratio does. Fantastic. Now, let us summarize what we did. We derived what f of k in its closed form is. It's 1 over the square root of 5 times phi of k minus phi bar of k, where phi is the golden ratio. And that's the whole video. In this video, I want to dedicate it to people that love math, and I think the motivation to do math is to discover all these patterns that underlie within our site, right? The Fibonacci numbers, we all know it correlates with the golden ratio, but have we ever wondered about writing the nth Fibonacci number in terms of phi? Well, that's the end of this video, and thanks for watching, and see you in the next video.